Virtual threads in Java are the biggest revolution since Lambdas. They are fast, lightweight, and built for the cloud era. You can now create millions of concurrent threads without blowing up your server, making your application insanely scalable and ridiculously cost-effective as well. If you are a Java developer, this is one game-changing feature you absolutely need to know. And the best part? I will reveal it in the video. Stay tuned. For the time being, forget about multi-threading and imagine your computer has just one CPU core. Still, you're able to run multiple apps like Photoshop, MS Paint, Notepad, all at the same time. How is this possible? Well, even though there is only one core, your CPU uses something called time slicing. It quickly switches between tasks, giving a small time slot to each app. Like first a little time to Photoshop, then Paint, then Notepad, etc. And it keeps rotating between them very fast. So fast that it feels like everything is happening at once. But technically, only one task is running at any given moment. It's just switching super fast so we don't notice. Now what if your computer has multi-core processor, say 4 cores? In that case, things get even better. Each core can actually handle one task at the same time. So with 4 cores, your system can truly run 4 different tasks in parallel, one task per core. And even these individual cores can do time slicing, so they can switch between multiple tasks as well if needed. So overall, your system becomes much more powerful in handling multiple things. Now let's talk about multi-threading. If your program is doing just one thing at a time, it's called single tasking or single-threaded program. But modern programs often need to do multiple things simultaneously, like downloading a file while showing a loading spinner or reading a file while updating the screen. To do that, your program can split itself into smaller parts, which can run independently. That's where the concept of threads comes in. But we'll get into that in just a bit. Before that, let's take a real-life example. Imagine you're using a browser like Chrome. At one moment, one part of the browser is downloading a file. Another part is rendering a web page. And another part is playing a YouTube video. All these are happening together. That's the power of breaking tasks into smaller parts that can run independently. Each of these independent tasks inside your program is handled by a thread. Threads allow different parts of your program to run at the same time, either truly in parallel or through time slicing, depending on how many CPU cores are available. If your computer has more threads than cores, which is usually the case, then CPU switches between them using time slicing. So they are not truly running at the same time, but it feels like they are. But if there are enough cores, then threads can run in true parallel, one thread per core. And the CPU core doesn't really care whether the task it's running comes from different programs or the same program. All it sees is a queue of tasks to execute and time slices between them. Now let's say you want to run some task in your Java program in a separate line of execution. So what happens when you run this statement is, well, the JVM asks the operating system to create a new thread for this task. This thread is managed completely by the operating system, and that's why we call it a platform thread or sometimes an OS thread. You might also hear terms like native thread or kernel thread. They all refer to the same thing, a thread that depends on the operating system to handle its entire life cycle. So what exactly does the OS do for this thread? Quite a lot actually. It creates and destroys the thread. It decides when the thread should run. It switches between threads called context switching, and it allocates memory and CPU resources for each thread. But because of all this is managed by the operating system, it comes with some heavy overhead. Each OS thread needs its own memory space, especially a chunk of memory for its stack. In Java, the default stack size per thread is around 1 MB. So if your application creates 10,000 threads, that's the stack memory alone with 10,000 MB. That's 10 GB of memory. That's huge and unnecessary in many cases. Now here is another problem. Even if you have multiple threads, only one thread can run on a CPU core at a time. When many threads are trying to run, the OS has to keep switching between them. This process is called context switching. Every time the OS switches, it has to save the state of the current thread, load the state of the next thread, and then resume the execution. All this takes time and uses CPU cycles. So context switching isn't free. It's slow and expensive. Now, because of memory and CPU costs, you can't create thousands of threads efficiently. If your app has many concurrent tasks, like server handling 10,000 requests for instance, traditional OS threads will cause performance bottlenecks. Imagine you're building a Java web server, maybe using Spring Boot, and your server needs to handle around 10,000 user requests at the same time. Now assume that each of these user requests does three things. It makes a database call that takes about maybe 200 milliseconds, let's say. It waits for a response from an external API, say a payment gateway API for instance. And once everything is done, it returns a response back to the client. Now typically in Java, each request is handled by a separate OS thread. But there is a problem here. While that request is waiting for a response from the database or from an external API, which are basically I/O operations, the thread is basically doing nothing. It's just sitting there, blocked, waiting for something to come back. But remember, this thread is still consuming memory and CPU scheduling power. Even though it's not doing any real work, it's still holding on to the resources. Even though threads themselves require resources, the operations they often perform do not. For example, making an API call or querying a database. It's not a CPU-intensive task. It mostly involves waiting for the response. So why use a heavyweight thread that consumes system resources just to wait? That's exactly where virtual threads comes into picture. By the way, if you like my style of teaching, do check out my courses. Link is in the description below. And if you want to become a full stack developer, you can check out the link in the description. Or at the very least, like this video and share it with someone who might benefit from this. Now let's continue. You can think of virtual threads as a lighter version of the traditional threads. Unlike traditional threads, which are managed by the operating system and consume significant resources, virtual threads are managed by the JVM and are much more lightweight. Internally, virtual threads still rely on traditional threads. When a client request involves a blocking operation like an API call or a database call, the JVM suspends the virtual thread and frees up the underlying platform thread. This will ensure that the traditional thread is not blocked unnecessarily. Once the response is received from an API, the JVM restores the state of the virtual thread and assigns it to any available platform thread to continue processing, like sending the response back to the client, for instance. Now here is the best part. As a developer, we don't need to worry too much about how virtual threads work internally. The beauty of virtual threads is that they behave just like traditional threads. And in most cases, the code remains exactly the same. You write the same logic, no reactive programming, no special APIs, just a different way of starting the thread. If the operation is blocking, like calling an API or querying a database, the underlying platform thread is freed by the JVM, and the virtual thread is parked, which means system resources are not wasted while waiting for an I/O operation. If the operation is CPU intensive though, the virtual thread will continue to run on a real platform thread, doing the heavy lifting as needed. In such cases, the performance is still similar to traditional threads because real CPU work must be done by the real thread. Well, while the shift to the virtual thread may feel very minimal at the code level, it's a game changing in terms of scalability and efficiency, especially for modern day enterprise applications that handle thousands of concurrent requests. With virtual threads, Java applications can handle massive amount of concurrency with minimal overhead, all without a complete rewrite.